The amount of carbon and sulfur in a material can have tremendous impact on its physical and chemical properties. Yet these elements can be very difficult to measure by direct spectroscopic methods. This is especially true when embedded in inorganic matrices such as iron and steel, cement, limestone, and glass or ceramics. But if the carbon and sulfur can be coaxed from their formidable fortresses, there may be a way to easily and accurately measure these elements. The answer? Heat, and lots of it, to the point of melting and combusting the material, forming stable combustion products. A sample of the material, chips, pieces, shavings, drillings, or powder, is weighed into a crucible and topped with a bit of accelerator. Induction furnaces use high voltage, high frequency AC power to induce an eddy current into conductive materials. The eddy current leads to joule heating, melting the sample. High frequency induction is fast, really fast. And because the sample is heated directly, it has a low thermal mass, keeping the surrounding area and components relatively cool. This allows temperatures of more than 2,000 degrees Celsius to be reached. While the sample melts, oxygen flows through the induction furnace. The carbon and sulfur in the sample react with pure oxygen, forming carbon dioxide and sulfur dioxide, which are much easier to analyze. The most effective way to detect sulfur dioxide is through UV absorption. The SO2 absorbs a portion of the ultraviolet light, resulting in a measurable drop in UV. This detection technique is much more efficient and faster than traditional IR absorption. The ultrasense detector is powered by a long-life UV LED source and boasts an ultra-wide linear dynamic range, staggering selectivity, a drift-free baseline, and a 10-time better signal-to-noise ratio. In much the same way that sulfur dioxide can be detected by observing its absorption of ultraviolet light, carbon dioxide can be detected using infrared light. Using a non-dispersive infrared sensor, specific wavelengths of the IR spectrum excite vibrations of the CO2 molecules in the sample gas and are absorbed. A drop in IR light is measured. Signals of CO2 and SO2 are recorded over time and integrated. Peak areas are directly related to the mass of CO2 and SO2 and is calibrated to the mass of carbon and sulfur in the sample. A fast and complete combustion is also vigorous and creates dust. Dust handling is important for analytical results, safety, and component lifetime. Improvements in equipment design have not only increased efficiency in collecting combustion gases, but they've also improved containment of the dust and debris, making cleanup faster, quieter, and more efficient, and decreasing operating costs associated with replacement of worn components inside the combustion chamber. As we push to make better, stronger materials, more efficient use of natural resources, and as environmental effects of converting and manufacturing become increasingly critical to consider, accurate and reliable measurement of sulfur and carbon become imperative to understand. Modern instruments make collecting this data clean, easy, and fast.